Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at question number 8 on our 2009 Euclid contest. And we're done with the light bulb questions. There'll be no more of those. The last one was in 7. And we've got 2 written questions, A and B parts here. So in A, ABCD is a trapezoid with parallel sides AB and DC. Okay, and apparently we've got lengths X and Y. Also, BC is perpendicular to AB and to DC. The line PQ is parallel to AB, and therefore parallel to DC, and divides the trapezoid into 2 regions of equal area, but they don't tell me what that area is. If AB is X, DC is Y, and PQ has length R, prove that X squared plus Y squared equals 2R squared. Okay. Let's copy our picture down. It's quite interesting that they mentioned perpendicularity here. Does this not work if they don't have a perpendicular side? I feel like it should still work. Where would I use perpendicularity? Although maybe we drop a height here and have a right angle triangle, and maybe another one here. Things to think about. Now they mentioned the area is the same for both of them. I don't know what that area is. I was going to call it A, and then I realized I've got point A here. And we also got P and Q. So let's be fun, and let's say AB, QP, and PQ, CD have area, I don't know, doesn't matter. Let's pick a letter, Z. Why Z? Because I felt like it. It doesn't really matter. Actually, let's not make it Z, because my Zs tend to look like 2s. What would be good? How about H? Yeah, H is pretty uncontroversial. Okay, so areas are H. Now, they mentioned their trapezoid, and already I'm starting to think, well, what's the formula for the area of a trapezoid? Well, if I have the height of a trapezoid, and I have the lengths of the parallel sides, the area of the trapezoid is 1/2 sum of the parallel sides times H. Well, I don't have heights here, although I could make heights, so I could drop an E and an F here. So I'd probably say something like, let AE and PF be altitudes, and I'll call the lengths G and little h respectively. Okay, little h and capital H don't look too much alike, so that's okay. So I'll say length G and H respectively. Alternatively, I guess I could have just said BQ and Q. Actually, I think that would probably be a lot easier. So, still call them G and H. So let BQ equal G and QC equal H. These are altitudes, or heights, of the trapezoids. So I suppose I can say, well, H is the area of ABQP, so that's 1/2 GX plus R. And this is also 1/2 HR plus Y. Okay? So now I'm starting to relate things together, but this is still too many variables. I've got 2 equations, and I've got 5 variables. These G's and these H's, I'm being asked to prove an expression here with X, Y, and R. First of all, I'm not seeing them being squared right now. We'll cross that bridge when we come to it. But I'm not seeing any of the heights anywhere in here. So I need to find a way to get rid of the heights. And I can use this equation to get G in terms of H, R, X, and Y, but I don't think I can get rid of H, so I have to sort of think about, is there another expression? And absolutely there is. Let's get some red here. Because there is the big trapezoid. And its height is G plus H, and it's got X, and it's got Y. And its area is going to be 2H, because it's 2 copies of H put together. So I'd probably say, area A, B, C, D is 2H. So 2H is 1/2 G plus H, X plus Y. Okay. What to do now? So I guess I can bring the other equations over. I'm going to say, I'm going to summarize these. I'm going to get rid of the halves. So I get GH, X plus R. Actually, 2H, X plus R is G. 2H, R plus Y is H. And then 4H is 2H, X plus R plus 2H, R plus Y. I'm just plugging them into this expression here. Times X plus Y. Okay, dividing by 2H on both sides, I can just get that 2 is 1 over X plus R plus 1 over R plus Y. X plus Y. So the area didn't really matter, which is good. And the area had nothing to do with it. And now let's multiply by X plus R, R plus Y. This is going to get 2X plus R, R plus Y on the other side. And then we'll have R plus Y, X plus R, and all this is times X plus Y. Okay, let's expand this out. So 2xr plus 2xy plus 2r squared plus 2ry is rx plus ry plus yx plus y squared plus x squared plus xy plus rx plus ry. Okay, that was a mouthful, but Rx and an Rx cancel out with these two. Ry's cancel and the XY's cancel. So what do we have? 2r squared is x squared plus y squared, which is exactly what we were asked to prove. Okay. So that squares away A part. What have we got for B part? A circle here. Alright, in the diagram, AB is tangent to the circle, so immediately, without reading any more, I'm drawing a perpendicular with the radius there. To the circle with center O and radius R. Okay, the length of AB is P. Point C is on the circle. D isn't. D is inside the circle so that BCD is a straight line. Now we're connecting it up to OD for some reason. If BC, CD, and DO are all length Q, prove that Q squared plus R squared equals P squared. Now this almost looks like it could be a trapezoid, but I can't guarantee that OD is parallel to AB. So the question 8, the two parts are geometry, but I don't think they're related. Well, my gosh, do they look like they could be. But I suppose if C were lower, then, I could have something like this and have it still work out. So I think there's lots of choices for C that could produce an appropriate D. I wonder what the locus of points of that would be. Okay, what could I do? I want a p squared, q squared, and r squared. P squared. Well, the first thing that pops into mind is the sort of power of a point or intersecting chords result. So if I have a circle, say O and A here, and an external point B, and AB is tangent to the circle, and I take really any other chord. So we could have C. We couldn't necessarily have D because D is somewhere around here, but actually, let's write this a bit more generally so it's a bit clear what result I'm using, just in case you haven't heard of power of a point. Okay, so power of a point theorem comes in a couple flavors. We don't actually need O there. If I have a point inside a circle and it's the intersection point of two chords of the circle, which is why this is sometimes called intersecting chords theorem, although I prefer power of a point because it places more emphasis on the point and its relationship to the circle rather than the chords, but other people call it different things. Turns out xp times pw is the same as yp times pz, and it doesn't matter where x, y, w, and z are. As long as they are chords and they intersect at p, this result is true. These lengths have the same product. This is sometimes called the cross ratio, I believe, okay, in older geometry books. And it's a shame they don't teach a lot of circle geometry anymore, because this is a pretty good result. And it doesn't just work inside the circle, which is the part of the result that has caught my attention right now. Okay. If I have a point P outside the circle, and I have two chords, X, W, Y, Z, the same result still holds. X to W, P to W times P to X, which is longer, is the same product as P to Y and times P to Z. Now, where the tangents come in is if I have a tangent point, maybe call it T here, and PT is tangent to the circle, well, it's like a chord, but it doesn't have two distinct intersection points. And what happens is PT ends up pulling double duty. So it turns out PT squared is PW times PX, and that's the same as PW, or PY times PZ. So in our picture, we've got AB is tangent, so B is the sort of the power of the point that we're working with, and we've got AB, which is P, and we're talking about P squared in the result that we want. Okay, so for our picture, got A here, and B is out here. So if I had another chord, maybe we don't need the perpendicularity A there right now, although I suspect we'll probably need it at some point. If I had another chord that met B, then I could say P squared is equal to that sort of a product. Well, they tell me in the question that BCD is a straight line. So I might say something like extend BD to F. No, let's say E on the circle. I don't have an E yet on the circle. I will extend them. I'll use a little bit of color here. E. Okay. So then P squared, which is AB squared, is the same as BC times BE. And I know that that's Q times BE. But what's BE? So I got a Q here, Q here. If I knew what DE was, so BE is Q plus DE. So if I knew what DE is, I'd be all set. How can I figure out what DE is? Well, the problem is I don't know a whole lot about D, although I do know D to O is Q. could I use another parallel point, extend this guy out to F, extend this out to G? Is that too much, though? So could I say extend OD to F and G on circle with, let's say, OG, all right, with D on OF, just to make it clear. Although you should be including a picture when you're doing these things, but D on OF makes it very easy. Okay. Then CD times DE is the same as DG times DF. And that's Q times the thing I don't understand. And then what are these? DG is Q plus OG, and O is the center, and so OG, OF are radii. Ah, there we go. There we go. OF, OG are radii. DG is OG plus DO, which is going to be R plus Q. DF is OF minus OD, so this is R minus Q. So Q times DE is going to be R plus Q times R minus Q, which is R squared minus Q squared, difference of squares. So P squared is Q times DE plus Q, right? Go back to my picture. BE is Q plus DE. No, wait, BE isn't Q plus DE. It's going to be 2 Qs. Have I screwed this up? BE is Q plus CE, and CE is Q plus DE. So it's DE I still didn't know about. I think when I was extending my line, I wasn't paying attention. So it's 2Q plus DE. And now I know what D is. So we get DE plus 2Q. So this is Q times R squared minus Q squared over Q plus 2Q. It's going to be R squared minus Q squared plus 2Q squared, which is R squared plus Q squared. And we're done. Although, probably shouldn't put a box there. I've just been teaching all day, and I've been putting boxes at the end of my theorems, or my proofs. Yeah. P squared is R squared plus Q squared. That is what we wanted, right? Q squared plus R squared is P squared. Okay, there we go. That finishes up question number 8. So I guess we set our sights on our second last question, which will be question number 9, and I will see you for that next time.